Ever wonder how AI creates those mind-blowing images or videos that look almost real? It's not just magic, it's math and a whole lot of clever engineering. Today, we're breaking down a game-changing technique called Decomposable Flow Matching, DFM. That's making AI-generated media better, faster, and more realistic. Let's dive in. So how do AI models even start when creating an image? Think of it like building a house. You don't start with the roof or the windows, you lay the foundation first. Traditional AI methods try to generate images all at once, which is like trying to build a house while juggling bricks, nails, and tools. It's messy and inefficient. That's where diffusion models come in. They work by reversing a process where noise is added to an image, teaching the model to clean it up. But even these models struggle with complexity, especially when handling details at different scales. Here's the catch. Most AI systems tackle images as a whole, but real-world images have layers. Think of a photo of a sunset. There's the broad orange sky, the tiny details of clouds, and the subtle gradients in the light. Trying to handle all that at once is like trying to paint a masterpiece with a single brushstroke. That's where DFM steps in. DFM is like giving the AI a set of tools for each layer of the image. Instead of one model doing everything, it breaks the process into stages, starting with a rough sketch and gradually adding finer details. Imagine a painter who first outlines a face, then adds eyes, then textures the skin. DFM does something similar, but with math. It uses a technique called flow matching, which is like teaching the model to flow from random noise to a clear image, step by step. Here's the magic. DFM doesn't need separate models for each stage. It uses one model that handles all levels of detail at once. How? By creating a pyramid of image scales. The model starts with a blurry, low-resolution version of the image and slowly adds sharper details, like zooming in on a photo. This approach avoids the pitfalls of older methods, which either got stuck in too many steps or lost quality along the way. Let's get technical. DFM operates by decomposing the generation process into hierarchical flows. At each scale, the model learns to transform noise into structured data, leveraging a shared parameter space across all levels. This is achieved through a multi-scale latent space, where features are progressively refined. For example, the coarsest level might capture global structure, like the shape of a tree, while finer levels handle textures, like individual leaves. This decomposition allows the model to focus computational resources where they're most needed, avoiding the inefficiencies of monolithic architectures. The proof is in the pudding. When tested on massive datasets like ImageNet, DFM improved results by 35% compared to older models. It also speeds up training, which means faster results and less computing power. And here's the best part, it's flexible. You can customize how the image is broken down, by resolution, color, or even texture, giving creators more control. But DFM isn't just theoretical. A 2022 NOR-IPS study pushed its boundaries by integrating it with DiT-XL/2, a diffusion transformer architecture. Researchers split the process into two stages, a coarse denoising phase for structural elements and a fine-grained phase for textures. They found that allocating more training time to the first stage drastically improved overall quality, while the second stage required specialized refinements. They tested Tokenformer and LoRA wrappers to optimize efficiency. Tokenformer, while promising, lagged behind the standard DiT design. But LoRA low-rank adaptation proved revolutionary. By tweaking just a fraction of the model's parameters, they reduced memory usage without sacrificing quality. Even with high LoRA ranks, results closely matched fully trained models, proving the power of parameter-efficient fine-tuning. The study also explored expert models, specialized networks for each stage. While training separate models boosted quality, it came at a computational cost. Instead, they used fine-tuning to adapt the coarse model for fine details, striking a balance between performance and efficiency. This hybrid approach hints at a future where AI generation is both precise and scalable. So why does this matter? DFM isn't just a tweak, it's a leap forward. It's making AI-generated media more realistic, efficient, and accessible. Whether you're a designer, a filmmaker, or just someone who loves cool tech, this is a big deal. The next time you see an AI-generated image, remember, it's not magic. It's math, powered by ideas like decomposable flow matching. Thanks for watching. Hit subscribe for more deep dives into the cutting edge of AI research. Until next time, keep exploring.